Hello everyone. I'm going to talk about high-speed erosion of very special materials, so-called ultrafine grain materials. So I'm going to talk about the materials themselves, the problem of high-speed erosion, our experimental technique, and I will discuss some of our results. And also discuss some of our research plans, as this work should be considered as kind of introductory work into the problem of high-speed erosions of these type of materials. High-speed erosion might be often encountered in airline industry, as blades of jet engines are hit by particles, dust, sand, which cover the runways, especially in countries like Africa, Russia, Asian regions. And it's a huge problem, and engineers and scientists, researchers are trying to solve it somehow by optimizing shape of blades, construction of engines, by applying various coatings on the blades, and of course by optimizing materials which are used for the blades themselves. Our colleagues from UFA Air Institution have tried to produce a very special jet engine blade made of so-called ultrafine graded titanium alloy. So this work is like a next step which could make it easier to apply these materials to real industry. So let's talk about these materials, how they are produced. Well, by composition, these materials do not differ from the usual materials. They are put through a very special technique called severe plastic deformation. So the main idea of this method is to apply really high deformation on the material to change its structure and therefore to change its mechanical properties. There are many ways, many technical ways to do it. So I will talk about two of them. Well, mainly we use one of them, but I will discuss two of them. The first one is HPT, it's high pressure torsion, where the disc sample is put between two anvils which start to compress the specimen, and then they start to rotate the specimen and apply really high strains. You can make one rotation, two rotations, or 100 rotations. So you can imagine how large the strains are. The second widely used technique is called the equal channel angular pressing. In this technique, the cylinder type specimen is put into a press and is forced to pass through the angle. This is the angle. You can do it multiple times also, so you may reach incredible strains in the sample. Anyway, the main idea of these techniques is to apply severe deformation on material and to change the structure and to reduce the size of the grains and therefore to make the material stronger. In our case, we used the HPT technique, the high pressure torsion technique. This slide shows us the machinery we used in our laboratory. And for the tests, we used an aluminum alloy. Of course, it doesn't deal with airline industry, but this work should be regarded like a first step, and this material should be regarded as a model material. We just wanted to see what's going on there, because nobody did it, and that's the first time when these types of materials are tested for high-speed erosion. We used the following regime for the high-pressure torsion technique. It's quite common parameters. It's 6 GPa for the pressure and 10 revolutions which are made with a velocity of 1 revolution per minute. And all these these procedures were done at the room temperature. So as a result, we had a reduction of the grain size and the growth of the strength. And of course the growth of the micro hardness of the material. On this slide you may see the EBSD map of the material, and you may see that the grain reduced from 40 microns to about 1 micron. And this is how the samples look like after the HPT technique. So let's turn to the high-speed erosion testing technique. We used the wind tunnel for the erosion testing, but it's not the common wind tunnel which is used for cars or for planes. It's a small-scale wind tunnel, but by saying small scale, I mean that it has a very small nozzle. Actually, this setup might be placed in a school gym. It's really, really large. It consists of a compressor room, it consists of the particle accelerator, the feeder device, and the working chamber. The idea was to test two materials in equal conditions, the initial material and the one that went through HPT technique. For this, we decided to develop a special holder that would hold two samples simultaneously. You may see this holder in this picture. So the samples were semicircles. The left semicircle was the initial material, and the right one was the one that went through the HPT technique. As for particle velocity, the setup provided us opportunity to reach about 200 meters per second. And for particle material, we used corundum of the size of around 100 microns. But the next question is how one can assess the erosion resistance. Well, the common techniques apply the measurement of mass loss or reduction of thickness, but here we used a bit tricky method. We measured how the surface roughness of the material changed. The surface roughness is a parameter which actually is an average of the distortion of the profile of the sample from some line. But to measure correlation between surface roughness and actual damage of the material, we investigated the samples with a microscope to see how the damaged layer correlates to the surface roughness. So now we're going to our results of the investigation. A very important question when you study the high-speed erosion is how long is the experiment, how long the specimens are treated by high-speed erosion. For this we tested, made experiments of several duration times, and we found out that after 10 minutes the surface roughness doesn't change much. So all other experiments were made with a duration of 10 minutes. This is the main result we have. The upper line depicts dependence of the delta of surface roughness. The delta of surface roughness is simply the difference between the initial surface roughness and the surface roughness after the erosion treatment. You may see that the change of surface roughness for the initial material is almost twice higher than for the material that went through the HPT processing. By fitting these points with the straight lines, we also managed to find critical velocities of particles, which are supposed not to change the surface roughness of materials. Of course, it's a very rough method. This is a very rough method, but it provides us some general information about threshold velocities of the particles. So we simply intersect these lines with the zero roughness change, and we obtain critical velocities. What about correlation between surface roughness and the damaged layer? So here you may see some microscopic photographs of the specimens, And we found out that the thickness, the ratio of thickness of damaged layers is almost equal to the ratio of the surface roughnesses of the initial material and the ultrafine grain material. So we may say that at least for low velocities of erosive particles, surface roughness might characterize the resistance to the high-speed erosion. So, of course, for the future research plans, we are going to move to titanium alloys to be closer to airline industry. And we're going to apply more common techniques of mass loss and the thickness reduction. Here you may see some our first efforts to measure mass loss versus particle velocity for the titan and the surface roughness versus particle velocity. We're also going to perform FEM simulations of the erosion of turbine blades. You may ask why we haven't started with the mass loss investigation with our samples. Unfortunately, we made really small samples, and the difference between two materials was almost insignificant, and it was of the same order of as the error of the measurements. But now we are going to make larger samples, and we are going to apply more common mass loss techniques. So thank you for your attention.